8 out of 15. Awesome. And let's get, oh, that's convenient. It's already pointed to the right place. So far good, 9. That's good. What am I doing next? Chat room. I'll get that down there so it can annoyingly interfere. Okay, chat box is this guy. All right. And that should be enough control. 10 people. That's probably good enough. So I will sign into my Blackboard. And let me get the correct course. You guys are section 1. Be sure the lesson's there. It is. Okay, very good. So I will formally start. Good evening. Welcome to lesson 6 of ce3372. Water systems design. Today's lesson focuses on pumps and pumping. Again, more fluid mechanics review, but relevant for the subject. So we'll take the content link to the lesson description. So we're going to review pump types, discuss a little bit about pump curves, refresh a little bit of the concept of a system curve, discuss some net positive suction head considerations, pump power, and illustrate some online tools. And the notes section I know aren't good because they were there for the morning, so these 2 links don't exist yet, but I have stuff from 2018. I'm pretty sure it covers the same material. Those links exist, and there are no spreadsheets associated with this and no supplemental data. Okay, so we shall begin. There's a series of readings here that are available to you. The first one is called Pump Selection, and it discusses how to select pumping equipment, at least from the hydraulics consideration. And you can read that. There is also, by the same author, suction and discharge conditions, and that's this is largely important for the hydraulics of the system to be available to operate correctly. And I'll actually be using this equation that's sideways, and this is a good reading to do on your own at some point. An alternative explanation is from a book called Basic Hydraulics by Barbara Hauser, and it discusses the issues of priming pumps, cavitation, and has some good diagrams, and discusses about net positive suction head available. The last 2 examples, one is a lift station design. This is a 2011 manual from the City of Houston as representative of a lift station design manual, and literally goes through almost everything you would need to be able to do to design a lift station, including the hydraulic machinery selection, as well as the vault box in which it would be placed. And then the last one is lift station design from the National Hydraulics Institute of the Federal Highway Administration, and it has a whole presentation on stormwater pump station design. The basic principles of the highway design or an ordinary lift station are pretty much the same, and so either of those references would be good if you had to flat out design an entire lift station. So I'll leave those readings for you to do on your own. I recommend that you glance through all of them, if for no other reason than to become familiar with locations of specific pumping information. Moving on with the lesson, so I'll talk at you for a while. This is part one. We'll discuss what a pump is. So it's a device that imparts energy into a liquid, and it's used for lifting. In our case, the liquid is water. It's used to lift water from lower elevations to higher elevations, and characteristically the places that do that are called lift stations. So lift station isn't just the pump, it's the infrastructure that supports the pump. The other contextual use is to add pressure. Those are called booster stations. And whether you call them lift or booster stations is really just a semantic choice. They're the same thing. They have infrastructure to support the pump and its hydraulic connections. The gas phase equivalent of a pump is a compressor, and the similarities between a compressor station and a lift station are quite common. They have a lot of commonalities. So the photograph is some generic pump, and the main components here are the motor, or whatever provides the mechanical energy that the pump housing and the pump inside it impart to the water. In this photograph, there's a flange here to the right. You can see the inlet hole here. This happens to be the suction side. Water would enter through this hole into the center of the pump housing, and then there's a spinny thing inside called an impeller, which throws the water from the center line out towards the edge, and then that's captured by the housing and directed to the discharge outlet. And here's the discharge outlet, another flange here, and then there's a hole there for the discharge. You can also see a fitting right here that I suspect in the case of this particular pump is a tap either for a pressure gauge, probably for a pressure gauge to be used to control the pump itself. Pumps range in size from really big. So here's a large axial flow pump. This particular one is a hurricane protection system pump. So it takes water from this dark area here, and when it's in service, there'd be water in here in the dark area, and then the pump impeller spins and pushes water out to the lower left corner of the screen, where the repairman here is either repairing the pump or eating a can of tuna fish. Given that he's under supervision, I think he's repairing the pump. They're probably making, looking at this, it looks like they're probably making some changes to either the controller system or a sensor that monitors the stability of this bearing right here. So this large thing here is a bearing. The drive motor is up here to the upper right of the picture. So that's an idea. That's a scale of a pretty big pump. So when they get it all fixed, this dude will get out, and they'll put the top housing back on it. They'll open the valves that are holding the water back from this hole, and then this will fill to some fill depth, which looks like it's right about here. So roughly at this guy's knee level is what the static fill depth of this system would be. And then this is turned on and it pushes the water away and draws more in. Pumps can also be quite small. So here are two photographs and one schematic illustration of very small pumps. This upper one that's in this person's hand, just from the look of it, to me, it's probably a type of a diaphragm pump, but it could be a little teeny weeny rotary pump. The configuration actually almost suggests rotary pump, but what's more important in the picture is the size of it. It's two joints of somebody's hand. This small pump fits in it. And going smaller still, this is most likely a infusion pump for bringing medicine to somebody, and it's a very small dual piston diaphragm pump. And so the medicine flows in here, and you can see in the illustration these two little cavities, and the electric supply would make this diaphragm move. The cavity would come in. It would change voltage polarity and push it to the next cavity, change polarity again, and that would push it out of the pump. Very small. So small, big. They obviously move different quantities of fluid, but the conceptual operation principle is the same for either one. So pumps come in two flavors, positive displacement and variable displacement. The positive displacement is characterized by the volume of fluid displaced each cycle is the same, more or less regardless of the system head or pressure. The trade-off for that seemingly desirable situation tends to be lower flow rates, although it can produce much higher heads than a variable displacement pump. A variable displacement is exactly what its name sounds like. The volume of fluid displaced for each cycle of the pump, or each RPM, depends on the static head and pressure that it's operating into. So if you can imagine a vertical tube goes up to the ceiling, filled with water, and at the top of the tube there's a little hole, and at the bottom of the tube there's a hole, and we attach a pump to the hole at the bottom of the tube. The variable displacement pump, the flow rate it can produce is hugely dependent on where that hole at the top of the tube is located. Whereas a positive displacement pump, as long as it has enough energy, will force fluid through the system or break things. And so that's the big difference. I've got some pictures of them coming up. In terms of positive displacement pumps, we'll look at a couple of them. The ones you're likely to be familiar with are screw pumps or Archimedes pumps and reciprocating pumps. And then we will actually we'll look at a video of neither, of something called a folding impeller pump, which is another type of fixed displacement pump. And then in the variable displacement pumps, the categories are centrifugal, axial flow, and a jet pump, which is a think of a mixed flow consideration. Actually, I just realized this bullet item is wrong. Jet pumps are indeed mixed flow, but that's not what's meant by a mixed flow pump. So let's move on for the Archimedes or the screw pump. So what these have, at least in this depiction, is there's a trough or a half circle channel, if you will, and a pump, a shaft with blades welded to it that looks like a giant screw is laid in this trough. At the bottom of the trough is a bearing to hold all the weight of this giant screw, and there's a sump down here, and so water will enter this sump and fill up to some level, and then when we turn this thing on, as it starts to spin, this screw blade will grab a portion of water and steadily move it up this incline until it gets to a discharge side. So here's a drawing sketch of the same thing. So this is the trough, or the half circle, if you will, that this screw is sitting in. There's a bearing at the bottom. The bottom bearing's purpose in life is pretty much to support the weight of the pump and water when it's in operation. And that presents some engineering and operation challenges, because if the water is unusually corrosive, the bearing might not last very long. Alternatively, it's going to need very frequent maintenance. One of the operational challenges of these pumps is usually you would design the controller, the PID controller, to maintain the water level just below the bearing, so it just catches the bottom edge, and that way the bearing can be kept out of the water and it lasts longer. Another variation of this design is, instead of these flights or the screws being on the outside of a rotating shaft, we take a hollow shaft and we put them on the inside. The advantage of that, there's certain mechanical advantages in terms of both the thrust bearing and the operational range for the pump, but they work identically. And then when the water is lifted up to the discharge side, it enters the discharge trough and goes along its merry way. These kind of pumps are in use. They're more common than you might think. They're really good in flood control and hurricane systems because they can be left alone, turned off for long periods of time. As long as there's a monthly visit to check that the bottom bearing is still functional, bump the motor to be sure nothing is seized up, they can be turned on when they're needed. They're also used in wastewater plants, not because they're turned on as needed, because wastewater is made all the time, but because these can handle large debris and still function. So if somebody was able to flush a teddy bear down the toilet, this pump could easily handle a teddy bear without damage or without clogging. It's also quite possible a teddy bear could get through a large centrifugal pump. It would be in a terrible condition afterwards, but any teddy bear that's been floating in the sewage for a while, you kind of want to leave it there. Another example is something called a progressive cavity pump. So that, this at first glance looks entirely different than the screw pump, but at a more careful glance, we see that this undulating rotor, so it's a piece of metal that rotates around. It has these, in this drawing, a sort of an extended sine wave shape, and then it's sitting in a housing that has cavities the same shape as the rotor, is pretty much just like a screw pump. The stator, or the static part, that has the cavities plays the same role as the trough, and the rotor plays the same role as the revolving shaft. Now these kind of pumps are used for very viscous materials. So dewatered sludge, for instance, or very high viscosity oil field produced water, and are used in those cases. Peanut butter would be pumped through something like this. And then the last positive displacement pump that I have an example of is a piston pump. So we have a housing called the cylinder, and this piston moves up and down in the cylinder. When the piston moves up, the volume inside the cylinder is increased. That creates a slight suction which pulls this ball valve down into its seat so there can be no backflow, and lifts this ball valve up so that material can enter the now recently vacated volume. When it gets to the top of the cycle, it changes direction and pushes down. When it pushes down, material tries to flow away from the cylinder. On the right side, that pushes the check valve down into its seat. It prevents backflow and raises the discharge check valve and lets the liquid go on its merry way. The photograph at the right is an example of a piston pump that many people have in their household. And it's supposed to be a little funny, but it's also legitimately a simple piston pump. When the toilet bowl plunger is placed over the offending toilet bowl that's no longer draining and pushed, you're taking a cavity and making it smaller. That imparts a lot of pressure, and you hope that will push whatever the clog is over the siphon and go on about its merry way, and your toilet drains. And if you're lucky, it happens the first time you push. If it doesn't, you're dealing with toilet crap. You can usually get it to work in a couple times. So clogged toilets are messy. Now this particular one's really special because it has a 6-speed transmission handle on it. So you can handle anything from ordinary clogs all the way up to log jammers. In the variable displacement pump world, their characterization is based on the relative direction of flow from the water entering the pump to how it leaves the pump. So starting with the middle figure here, an axial flow pump, the axis of rotation, which is this purple arrow, is also the direction water enters the pump and leaves the pump, or at least leaves the impeller area. So that's axial flow, or sometimes they're called propeller pumps. A radial flow, or a true centrifugal pump, the water enters the eye along the axis of rotation and leaves the impeller at the radial periphery and 90 degrees offset from the axis of rotation. A mixed flow pump is a little of both. The mixed flow pumps are almost anyway, the water comes in mixed flow and leaves at a slight angle, and then there's a portion of the pump housing that will redirect this purple arrow into the next stage of the mixed flow pump. So the mixed flow pumps are usually several stages of these impellers with several stages of stators. And the big gain from a mixed flow pump, as opposed to an axial flow or a true centrifugal pump, is they can be made in smaller diameters for a given flow rate than either of the other two. Now that price comes at a stack of impellers. So there's 1, 2, 3. There's a bunch of them stacked up. But these are desirable for submersible use, like down a well bore, because they don't have to have very big diameter. I mean, we're not talking teeny diameters. They're 4 or 5 inches in diameter. whereas a propeller pump is several feet in diameter, and a centrifugal pump is at least 6 to 8 inches in diameter at the impeller, and with a housing it gets greater diameter still. And so that's the main difference mechanically. Now I wanted to take a couple of moments to look at 2 YouTube videos. Let me do that one. And this one's already queued up, so we're first going to watch a video on the impeller pump, and we didn't want to watch halfway in the video. I want to get kind of near the front. Okay, so these
That's why Chegg Study Pack empowers you with homework solutions and expert Q&A.
So there's your introduction to positive displacement and centrifugal pumps. The eye that they were talking about in the Kirloskar presentation is the inlet. So it's called an eye for, I don't actually know why it is. It's just like the eye of a hurricane. When they were talking about the increasing area in the direction of flow, this diagram here I think does a better job. The impeller is circular, so it subtends a circle, and the housing is not circular. It kind of looks it from the outside, but it actually is an increasing radius curve, so that the distance from the eye to the left edge in this diagram is smaller than the distance from the eye to the right edge. And that's how the water, when it has the added centrifugal energy, is directed to the discharge pipe. Axial flow pumps, as mentioned earlier, are really big propellers, and these are used in high flow, relatively low head applications. So an axial flow pump can produce enormous flow rates. The one in the photograph shown here during installation, here's the suction side, discharge is up. This pump here is the size of a pickup truck, not quite as wide, but certainly the same length, and weighs several thousand pounds. And to give you an idea of scale, the sump is 8 feet deep from this lip right here, this curb. So that's a good sized pump stuck down in there. This pump in the photograph can move 20,000 gallons per minute into an 11 feet of head. So not much head, so it can only lift it 8 or 10 feet, but it can lift 20,000 gallons per minute 8 or 10 feet. Another perspective is that pump could probably drain the lake in Ransom Canyon in less than a week. Moving to part 2, we're going to review some concepts in pump selection. So this is largely lifted from that first reading I showed you by Walker, and to give some guidance on how we choose a pump in practice. So we specify the design conditions. By that, the network we're going to attach the pump to, and we specify design flows a lower flow and a higher flow. And to come up with those, that's when we do that what if analysis. What if the valve is left open? What if the pipe breaks? What if the float valve fails? So that was what we visited last time in class. And then we can prepare a system curve, which is a plot of the total head required by the hydraulic system as a function of discharge. Once the system curve is prepared, we can select a pump curve from a manufacturer and superimpose them on each other on the same scale. And if and where they intersect is called the operating point. And that would be the actual working conditions we would expect the hydraulic system to behave at. So system curves, here it's drawn. I mean, that's not necessary all the time. But so this system curve in this drawing depicts the amount of energy that's required to maintain a steady flow rate under the supplied conditions. And the vertical axis is total head, which is elevation head plus head losses. So in this system curve here, there's 3 points at 0.1 units of flow, 0.2 units of flow, 0.3 units of flow. And in this case, it's showing that at 0.1, there's about 32 units of head required. At 0.2, 36 units of head. And at 0.3, 41 units of head. Now there's an interesting point right here where the flow rate drops to 0. So imagine we're moving down the curve. We're decreasing flow rate. When we get to 0, we find that we still have to supply head to the system, otherwise everything will leak out. That's called the shutoff head. The required head when the pump shuts off, when the pump flow rate shuts off. And an analogy to that would be a car with an automatic transmission on a stopped on a hill. As long as the hill is not too steep, you could release the brakes, and the idling car engine generates enough energy that the automatic transmission will hold the car in place. And how that's analogous is the car's not moving, so the flow rate's 0, but we're still using up energy. It's still burning gasoline. It can't do that indefinitely. System curves are created something like we're about to illustrate here. Now, if the system itself is complex, a hydraulic network, for instance, we probably wouldn't develop a system curve by hand per se. We'd use a simulation model, and we would put different pumps into the simulation model to assess whether or not they would work sufficiently for our application. But let's examine this picture right here. So here we have a reservoir whose pool elevation is 200 meters, attached to reservoir 2, whose pool elevation is 230 meters. So there's 30 meters of lift required to raise water from reservoir 1 to the top of reservoir 2. And they're connected to each other through this 1,000 meter long, 40 centimeter diameter pipe, which has a known friction factor of 0.015, and there's a pump in the system. So if these were just two reservoirs connected with pipes, we were pretty sure that the water would flow from reservoir 2 to reservoir 1. So the only way to make it flow from reservoir 1 to reservoir 2 is to add energy, and we do that with a pump. If we chose to write the energy equation from a couple meetings ago and rearrange it, we would find out that the total energy at 1 plus the added head at the pump equals the total energy at 2 plus the head loss going from 1 to 2. And that equation itself can be rearranged as shown here to the added head of the pump, meaning that the energy the pump has to supply is equal to 30 meters of head plus whatever the head loss is. That equals 30 plus FL over D plus the entrance coefficient, bend coefficient, exit coefficient times Q squared over A squared to the 2G. And if we perform all the indicated arithmetic with these particular numbers, we come up with the added head of the pump for this system to work is equal to 127 q squared plus 30. So the shutoff head for this system is 30 meters. That's when q goes to 0. And any flow rate bigger than 0 is 30 meters plus whatever energy is required to overcome friction. And here's the same relationship again. I'll leave that up for a second. The concept of shutoff is important, and it's easy to forget. I occasionally forget it, and that's the whole point of doing analysis before you actually commit a design to getting built. So we're going to look at a pump curve, and what a pump curve is going to do is it's going to relate added head of a pump to flow rate. And if you can think of the pump curve as an equation, very much like this, except it's going to be q squared minus something, we could put it on the left-hand side and solve for the value q that makes the right-hand side equal the left-hand side. That's called the operating point. The information that curves include typically is discharges on the x-axis. The total dynamic head is usually on the left y-axis. Pump power input is usually on the right y-axis. Pump efficiency appears as contour lines, as percentages. Somewhere it states the speed of the pump that was used for making the curve and the net positive suction head required for the pump. As an example, here's a particular pump, a Southern Cross 125 by 80 to 200 pump. So that designation is the manufacturer's designation. And let's look at the different parts of the curve. So up here in this legend, it's telling us that the speed that the pump operates is just shy of 3,000 RPM, and that's what was used to make these curves. The pump has an inlet diameter flange of 125 millimeters and a discharge nozzle diameter of 80 millimeters. So this pump has a bigger input size hole than output hole. And it uses the number 2 shaft module, which is a manufacturer's designation. Remember the video where it showed the pump housing. So in general, the pump housings are, a manufacturer doesn't make many different kinds of pump housings. The way they change performance is by putting different diameter impellers into a single housing. So if we want to operate at one behavior, we can put a 180 millimeter diameter impeller, and this particular housing can accept up to 228. Now you can't have different ones in there at the same time. This is just a way of not having to have 5 plots, among other things. So let's look at this lower line. So that corresponds to a 182 millimeter impeller housed in the 125 by 80-200 housing. The solid line here is the pump performance curve, and it's a plot of head on the left versus volumetric flow rate on the horizontal axis. For instance, at 30 liters per second, that particular impeller will produce about 40 meters of total head. So that might have been a good pump for our Africa case. If the flow rate's increased, in other words, if we want greater flow, we have to accept lower head. So when we move up to 60 liters per second, pretty much doubling the flow rate, the added head that the pump can supply drops more than double. It drops to about 18 meters of head. Let's go back to 30 liters per second. If 40 meters of head isn't sufficient for our application, one of our options is to increase the impeller size. So if we go to a 194 millimeter we get about 48 meters of head. If we go all the way up to a 228 millimeter impeller, we can get almost 70 meters of head. So changing impellers moves up and down in this diagram. The other key features of this pump curve are these contour lines, 40%, 50%, 60%, 65, 70. Those are the mechanical efficiency of the pump, or you can think of it as energy into the motor produces on the 70% curve, 70% energy to the water. So the sweet spot for this particular pump is right in this region here in terms of efficiency. We're in the 70% and greater efficiency when we're in this region right here, where the cursor is circling around. And right here kind of is dumb on a video, so I've got to assume that you can see my cursor moving. Say for instance we had a 205 millimeter diameter impeller and we're operating at 46 liters per second. That puts us right about there where the cursor is. That would be operating at 75% efficiency, which is about the best we can do for that impeller. And that would be a efficient operating point if that's what we wanted. There's also these dashed lines here. Those represent the input power requirements. So for example, going back to that sweet spot on the 205 millimeter diameter, where we're producing 46 liters per second at 48 meters of head, the input power requirement is just a little bit under 30 kilowatts. The last part of the curve that I want to bring your attention to is the net positive suction head required area. So that's plotted down here on this particular curve. The net positive suction head moves around on pump curves. So sometimes it's up in the, it's usually in one of the corners. Occasionally, but only rarely, is it actually plotted in the main body of the curve. So in this one, these are the suction heads that are required on the suction side for a 228 millimeter, the biggest impeller, and 182 millimeter, the smallest impeller. And so let's go back to our 75% operating point, and that was on the intermediate impeller. So our net positive suction head requirement for that particular situation is somewhere between 4 and 5.5 meters of suction head. If we don't have that much head available on the suction side, this system won't work. So the pump curves themselves then get superimposed onto the system curve on the same axes. So the Q-axis and the H-axis have to have the same units and scale. And on this diagram, we have two pumps, pump A and pump B. The system curve appears as this solid line curving up. And we can immediately see from this plot that pump A is insufficient for this system. So as a single pump A can't supply enough head for the system to flow at any flow rate. Pump B, in contrast, can operate all the way from shutoff to this intersection. That's where that green dot's supposed to be. And everything in the shaded area is the range that pump B could operate in. And then once we go to the right of that, pump B doesn't produce enough head. Here's another representation of the same thing. In this case, the net positive suction head is up to the top. The pump curve, plotted in red, is superimposed on the system curve, plotted in green. And in this case, the intersection occurs at 9 meters cubed per hour, 58 meters of head. The corresponding efficiency at that point is around 75% efficient, and the corresponding required net positive suction head is a little bit more than 4 meters. We can use multiple pumps in parallel and serial combinations to adjust the performance to fit the system requirements. If pumps are placed in parallel, it increases the flow for a given head difference. If pumps are placed in series, it increases the head for a given flow rate. So here's a schematic diagram. Now it's not quite as simple as just putting them in series and parallel. There's a bit of hydraulic art involved in matching all the pumps so that they don't fight one another. But for a design class, it's sufficient just to assume that they can be added either in parallel or series. If we were to take this configuration in the drawing here, the composite pump curve of pump B plus 2 pumps A in series is shown by this solid line. It has this knee in it where pump B loses its capability to be useful. And so that would be the composite performance curve. In that instance, we could have this system curve or that system curve accommodated. So the system curves, if they change, which they do with the age and added demand put on them, could be accommodated by that pumping system. So when we put pumps in parallel for a fixed value of head, the discharges add. So we have the discharge from the first pump, adds to the discharge from the second pump, adds to discharge from the third pump to produce this composite curve, or the outer envelope, which is labeled as the 3-pump curve. If we put the pumps in series, the curves stack. And so here's the single pump curve. If we put a second pump in, this is showing it that it actually doubles. There's the 2-pump curve, and then the 3-pump curve for 3 pumps in series. Now, real pumps don't add quite this cleanly. So the 3 pumps in series for a given flow rate isn't necessarily going to produce 3 H1, probably more like 2.8 or 2.7. But for conceptual design, just adding them is sufficient. And lastly, we will conclude the lesson for today with the suction requirements. Walker's book states that the most common cause of pumping failure is poor suction conditions. Cavitation, we saw in the video, occurs when the liquid pressure goes below the vapor pressure of the liquid, creates small bubbles which collapse upon themselves, releasing a great deal of energy, and they actually can break little pieces of metal off the impeller, and if they do it long enough, they can turn the impeller into a porous-looking cheese-like substance. Doesn't impel very good at that point. The damage happens fast in an engineering sense, but it's not instantaneous. So cavitation can destroy an impeller over a matter of hours to days, whereas other things that break on a system might take years to wear stuff out. So that's a big issue with cavitation. If the vapor pressure drops, if the water pressure drops low enough over a long enough distance, it will actually create an entire vapor bubble inside the piping system, and the system will cease to work. Like a vapor lock. For a piping system with a pump, cavitation occurs when the absolute pressure at the inflow falls below vapor pressure, and we find out what the vapor pressure is at a working temperature from one of our materials databases. So the requirements of a pump are that the liquid has to enter the pump eye under some non-negative pressure, and that pressure is called the net positive suction head. And the pump also has to be primed, or the first stage impellers have to be below the static water level in the suction pit at pump startup. So a pump will lift water out of a sump. That's not a problem, but that suction side pipe has to already be full of water when you turn the pump on. That's called priming. And there are simple to elaborate systems to prime a pump. Generally, once it's primed, you don't want it to become unprimed, because priming a pump is a pain in the neck. The requirements are provided by the manufacturer of the pump, and they provide a value for the minimum pressure the pump needs to operate. That pressure is called the net positive suction head required. The net positive suction head available is a calculation that we, the engineer, can make. And for the system to operate without cavitation, we need the net positive suction head available to be greater than the net positive suction head required. So how do we get the net positive suction head available? We can apply this equation here, which is taken straight from Walker's book. Net positive suction head available is the absolute pressure at the liquid surface in the suction pit of the liquid. That's a temperature and elevation dependent value, plus the static elevation of liquid above the pump inlet eye. Keyword above, minus the frictional head loss in inlet piping, minus the vapor pressure of the liquid at the pumping temperature. All those terms are expressed in units of head, so either in meters or feet, as the case may be. So we'll go through a brief example. So the problem setup is a 3,000 gallon per minute vertical turbine is located 4,000 feet above mean sea level. The water temperature is 90 degrees Fahrenheit, so it's pretty warm water. The suction bell is a 24-inch diameter, reducing to 12-inch diameter at the first impeller. That's giving us information to come up with a loss coefficient. The water level is never less than 8 feet above the first impeller. So what's the net positive suction head available under the worst imaginable conditions? So in terms of a step-by-step calculation, first thing we would do is determine the anticipated air pressure in feet of water. And we can apply the equation that the change in pressure with elevation is minus 1/2 pound per square inch per 1,000 foot of elevation change. We also can take into account that if there's a thunderstorm immediately above the pump station, those usually occur at about 85% of normal atmospheric pressure. So first we'll figure out what the pressure is at 4,000 feet, and then we'll take 85% of it to account for a storm cell being overhead. So the absolute pressure in that instance is 33.9 feet of water multiplied by 12.7 psi, which is the 4,000 foot air pressure, divided by 14.7 psi, which is the sea level air pressure, multiplied by 0.85 for a net result of 24.8 feet. So the absolute head expected in the wet well is 24.8 feet. That result is the product of 1 atmosphere in feet of water adjusted for 4,000 foot elevation change and adjusted again for the thunderstorm. That's our worst case air pressure. So if we're using an online tool, which we'll go look at shortly, we would enter the 24.8 for the absolute value of head at a liquid surface. Our next step is to specify or determine what the suction side pressure is in the water in terms of feet of water. In this case, it's 8 feet. the value is given to us in the problem statement. Again, if we're using online tool, we would enter an 8. Let's see what it says. Static elevation of pump inlet I above the liquid. So this actually should be a -8. Next step is the frictional losses on the suction side. We come up with 0.112 feet, and we obtain that from a head loss equation based on the nominal pumping rate of 3,000 gallons per minute and the reduced inlet diameter of 1 foot. We would get the minor loss coefficient from a table. The inlet velocity in this instance is about 8.5 feet per second. It's a bit on the high side, but that would work. And then we would enter that frictional loss here. And lastly, we would find the vapor pressure of water in feet, which is 1.6. We would get that from a table of water properties. And we would need to get the value for 90 degrees Fahrenheit. If we go to our table of water properties, our online, we find there's an 80 degree value and a 100 degree value. So we could get each of those values, 0.506 pounds PSI absolute at 80 degrees and 0.95 PSI absolute at 100 degrees. Average the two, because that should give us a good estimate of the 90 degree value. And then convert the pounds per square inch into feet of water. Easiest way to do that is to multiply it by 33.9 and divide by 14.75 psi for 1.67 feet. And once those values are determined, we can enter them into the tool, or we can apply the equation directly and come up with the required net positive suction head available, which is 31 feet. See if I have it up and running. So we get the water properties from here. So that was done in the example. And net positive suction head is here, at least in US units. And if we go back to our calculations, the absolute is 24.8. Okay, let me see if I'm getting the sign right, because it's a little bit tricky. H sub S in this online application is positive if the pump is above the water, so ours is going to be -8. Frictional loss was 0.112, kind of small. And the vapor pressure we had was 1.6 feet. Should get somewhere around 31 feet out of this. Sure enough, I do. And we've already got a lot of overestimation built into this, but if you're really nervous, you could decide that a 10% margin of uncertainty is justified, and that would take our net positive suction head available down to 28 feet, and we could use that when we specify our pumps. So that is, if we have a pump that requires more than 28 feet of head to operate, we would identify that as a potential pumping problem and either select a different pump or modify the suction condition. Lower the pump deeper into the pit, for instance. So that concludes today's presentation. We've discussed the next exercise that's due last few times. I'll refresh your mind one more time, if I can find it. So this exercise, you're going to estimate water demand for each of the invisible nodes, because it's not loading very fast, for each of the nodes. So this node, for instance, where the cursor is, supplies that house, that house, that house, that house, and that house. So it supplies 5 houses using these different definitions of demand from the readings, and essentially populate this table. You might find it useful to also estimate the elevation of each of those nodes, because you're going to need that later for a future homework and for the first report, first design report for the class. And if you feel so inclined, you'll want to measure the lengths of each of these pipes. So the node elevation, the pipe lengths are not specified in this particular exercise. You'll need them eventually, so you can choose this exercise to measure those now, or you can save it for later. That really doesn't make much of a difference. This is the same area that you built your topographic maps for, so getting the node elevations from the topographic map would be useful. And that's about all I'll say about that. Thank you for your attention, and we're actually coming to the end of the scheduled time. And I will see if I can get the chat window up. I can't. Yeah, no questions there. So if there's no questions, I'll go ahead and end the presentation. And I wish you all a good evening and a good day tomorrow and a good weekend. And also the what's now becoming the standard: be safe, try not to get sick, warnings, wear your mask, don't engage in risky activity, all the usual stuff. And I'm not trying to belittle it. It's certainly important, but you guys probably get 9 or 10 emails a day to the same effect. So at some point, we start to lose the message. Anyway, have a safe weekend, and I will see you on Tuesday. Thank you for your attention. I apologize for the Zoom thing not automatically sending you the link. And with that, have a great weekend. Goodbye.